Before we go further into the design for manufacture, it's time to do some basic safety and see how this thing moves, where we would expect the loads to be, and we can do that with the motion study. So the motion study kind of goes into whatever the last location was. So even if I go normal to the front plane, it's going to, when it does its calculation, return to that isometric view. So I want to replace the key, and these time keys are basically keeping track of each of the motions and things that we would want to have it go through each step. So across the top are our selections of animation or a basic motion that will give us kind of a force torque graph, calculating once we've applied some movement, how fast or how slow, and then outputting to an AVI file, and those files can get quite big, so it's nice, but goes through a lot of memory. So rotating the model, because we have the explode, not in the dynamic but in the default, I could have it explode and collapse over a period of time as it rotates, and it looks kind of neat. Import motion or motion analysis, and then the solar is how the sun tracks over the part, and the mate controller is available with save positions has been created. So don't really need to do the wizard. I would say tinker with that. It's kind of neat to perform the explodes and track. The auto key I think is on by default. I was pressing buttons and turning it off, so turning it on and turning it off. Adding and updating a key. Motor is what we're going to try to apply. A spring contact for like a cam if gravity is taking effect, and then the settings. So since I want a motor, we're going to just apply it to the cylindrical face. I went out onto the McMaster website and looked up some of the bushings for this size shaft and bushing. The RPM rating was at 120 with 600 pounds of force. So we're not expecting this to turn very fast, so the 100 RPM would be okay. And everything should update. And we'll leave it at that point so that when we calculate, it's showing the movement. All right, so once that's in place, really we can kind of reduce that down, and then we'll play from the start. And what I'm looking for, and if I needed to, it'd go slower on the RPM. But if I was operating this, what kind of shielding, what kind of guarding, what could I do to this base frame to simplify it in the manufacturing process, as well as to make this a safer unit. So rather than recalculate the motor, that was the start point, so let's play it at 0.25 times. So there is a little bit of pinch point in this area. The question is, if there was a finger or a toe or whatever that was to come into contact, would it be a pinch, or would it act as a guillotine and actually try to remove said finger? So the safety portion of it is this going to hurt somebody? All right, we've got enough gap over here and enough gap back here, but if I go to that other alternate assembly position where the 140 millimeter link is on the interior, puts us a lot closer. So those are some of the considerations that we would want to take into account. We can stretch that out and have it run for a longer period of time, have other items built into it. And then as we get to a point where we want to save the animation, are we going to use the image size? We're going to be able to output 7.5 frames. Right now it's picking up my screen size, so would want to probably reduce that down a little bit. And because it is a resource hit, may want to schedule for it to output. So our options are the MP4, Flash has pretty much gone away, series of bitmaps, JPEGs, would probably stay with the MP4 or the AVI files. And then once we told it to save, it would output, and then we could import that into other items. All right, so we go back into the model from the motion study. We would be interested then in our evaluation to look at the mass properties, and in its current position, we're at the dynamic. We can see its center of mass, and total weight is showing with all of our materials applied right at about 2.5 kilograms. So what's that, about 5.5 pounds? So center of mass, and then if we rotate and let it recalculate, then we're going to see that these center of mass will shift slightly, the moments of inertia will shift, and will give us a little more information if we need to perform any of those calculations. Going into something like the flywheel, and if you think of this more as a crank lobe, if we were to cut this off and bring it more into the shape, we'd have the offset. And so here we would be interested in how much off of the center of mass. So we're not gaining a whole lot of advantage with this this geometry and the cost of producing it. We have a little bit of the offset, and as I mentioned, if I was making those decisions, I would have to decide, do I want to trim some of this and put most of the mass at the arm, and what's that going to do to the motor to get it started. So we're about let's see, in the Y direction, 3.4 millimeters. So not too much off of center, but enough that it may give us some mechanical advantage. And then looking at the arms, we may want to take one of these. And I am at the professional level on this install, so if I go into the tools, we have the Express products, and for another simulation, if I hadn't already activated, it would have come up with a window that says you need to activate the Express. You log into your SolidWorks, My SolidWorks, and it gives you a code to punch in for it to build. So actually, I think I wanted the 140 millimeters. So let's go ahead and open that up, and we'll go back into the tools, Simulation Express. And so I'd be interested to see how thin this can be if there's a if there's going to be any issues with it. So we're in SI metric units, and it's saving the results into the temp folder. And if we're going to look for fixtures, we add a fixture. I'm going to say, what happens if this binds up and can't move? And our study would be this comes to a sudden screeching stop. What happens over here, and how does it affect this this load? So we're going to go next, and then if I add a force, we'll add the force on the interior, and this normal to, we need to select a direction, so maybe it's on the upswing. See if it'll let me pick the face. So since I need a direction, we'll get out of the force, and I'm gonna have to create something. And since I have all these cylindrical faces, it really wants a planar to work from. So we'll go into a sketch. Oops, not the hide. So let's go back and alright, so Shift Tab will bring that back. Make sure I get the sketch this time. Alright, so we'll go in for a line, and I need something for reference. And then we'll bring that over some distance. So I'm kind of thinking it's on the upswing, and don't know how far it's going to get. So we'll just set, and we can rerun this several times at different angles. So if we were to go to 170 degrees, that's just slightly off of the vertical axis. So, and picking the point and the cylinder going into the planes, we have tangent to the face and coincident at the point, so that this the sketch can drive that geometry. And so I go back in to the simulation. We can go back and edit that definition, and the selected direction will be across that face, and we can reverse. So doing the quick math, well, let's put something in there that we think will deform this even in steel. So what we'll look at is, I think in terms of maybe 10 pounds. So the 2.2 pounds per kilogram, 10 pounds would be a little under 5 kilograms. To make the 9.8 meters per second square to get to newtons, if we multiply that by 10, that would put us at 50 newtons. So put in 50 newtons. We have the direction going in the right way, and we can go to the next. And based on our material, it gives us the modulus elasticity, yield strength. We'll double check the material, and it was set to 1020 is fine. And then next. Shouldn't have to mess with the settings. For our purposes, we'll run the simulation. It'll go through the mesh. And there's some pretty good deformation, but we've got to preface that with, let's see if I'm going to be able to see it up here. Looks like that is 19, so let's see if we can turn this off and be able to see that the deformation scale is 30 times. So it's really not moving all that much. And so we'll expand that back out, stop the animation. Let's go to the stresses, and the stresses kind of naturally are at those points and are in millipascals. Yield strength at 3.5 plus 2, so we're not there yet. And the displacement in millimeters, 0.5 millimeters at the red. That's still some pretty good displacement, about 20 thousandths. Not a lot, but enough that if this came to a sudden stop, it might permanently stay deformed. And then the factor of safety, right now we're at the 1. So let's see, where do we go set that at? Part deformed as I expected, yes. There we go. Show where factor of safety is below 5. And then play animation. All right, so below 3. Oh, not available. Should just be updating then. And below 2. And pretty much if we have a 2 times factor of safety, we're in pretty good shape for this this geometry.